Welcome to the second session of question and answer on the topic gaseous state. The previous session we had seen just before this one, and this is the second part of that question answer session. We will move on to the questions. First question is, discuss the applicability of van der Waals equation in explaining real gas behavior under different conditions. Different conditions means under different conditions of temperature and pressure. Let's move on to the answer. Now, the van der Waals equation is P plus A by V square into V minus B is equal to RT, where P is the pressure, V is the volume, A by V square is the pressure correction and B is the volume correction, R is universal gas constant, and T the temperature in Kelvin scale. Okay. Now, let us move on to the expansion of the brackets. So, multiplying P into V, we will have it as P into V. Okay. Then P multiplied by minus P, it becomes P minus into minus V becomes minus PV. Then A by V square multiplied by V, both are positive. So, that will be A by V square, one of the square V will be cancelled and we will have A by V, which will be positive, and A by V square multiplied by minus B will be minus A into B by V square, and that is equal to RT. Now, taking RT towards this side, you can put this as and PV on one side, taking RT and the other terms together and keeping PV on one side. I can write this equation as PV, I am retaining on one side. Okay, so it is better I will consider all the terms taken to this side. So, that will be RT, and taking minus PV to the other side, it becomes plus PV, plus A by V goes to the other side, becomes minus A by V, minus AB by V square, when it goes to the other side, that becomes plus AB by V square. So, this is the equation we have arrived here. Okay. So, remember this expansion, that is just opening the brackets and expanding the terms, you will get such an equation. Retaining PV on one side and taking other terms towards the side of RT, we will get such an expression. Now, we are going to take the conditions. That is, we are going to check the applicability of van der Waals equation in different conditions. So, first condition is at low pressure. Now, what happens at low pressure? When pressure is low, volume will be very large. Okay. Then the terms PB and AB by V square, these two can be neglected. So, this is the expression we got, PV minus RT plus PB minus A by V plus AB by V square. Now, V is very large, this term becomes small, this term, that is PB, this is a correction for volume. So, this also becomes very small, and therefore, these two terms are neglected, and what we will have after that is PV is equal to RT minus A by V. So, this will be the resultant equation. What does it mean? Actually, for an ideal gas, PV is equal to RT. Now, at low pressures, the value of PV will be less than RT by a factor A by V. So, you will be having a lower values, and this explains, that is, when we plot a curve between pressure and volume or PV against V, we have seen that in most of the gases at low pressures, there is a dip and then gets the rising part. That is, when the pressure is low, we get a dip in the graph. Okay. So, it will, that is because this is PV is equal to RT. The value will be less than PV against V, not volume. Okay. So, there will be a decrease in the low pressure regions. Now, what happens when pressure is high? When pressure is high, V will be very small. You are giving very high pressure. B cannot be neglected. That is a correction for B, because B is very small and it represents the volume of the molecules. So, that cannot be neglected. And at the same time, A by V and AB by V square, they become almost equal because V is very small. Okay, here we have V square and here we have a product of A into B, and therefore, what happens is these two values will be almost equal, and you can see in this equation A by V is negative and AB by V square is positive, and therefore, they both, since they are equal, you can consider them as the difference to be equal to 0. That is, I can neglect this. The resultant equation will be PV is equal to RT plus PB. What does it mean? That is, PV is not equal to RT but greater by a factor PB, and this represents the graph. You can have that there will be a rising part. That is, when pressure is high, you have the rising part just because the value will be greater than RT instead of PV equals RT. Now, at low pressures, when pressure is low, volume will be very large. The pressure terms PB, AV and AB by V square can be neglected. V is very large. Okay. Now, at that conditions, the terms PB, A by V and AB by V square can be neglected. V is very large. When V comes in the denominator, that becomes a very small value. So, those two can be neglected. When V is very large, B also we can consider to be negligible, and therefore, the expression takes the form all these are neglected. And finally, we get PV is equal to RT, and this is the condition when real gases tend to be ideal. Now, we are going to the condition of high temperature. Again, when temperature is very high, volume is very large. Just as in the case, the volume is very large means B is negligible. Again, when the molecules are very far apart, they do not have intermolecular force of attraction, and therefore, the pressure correction also vanishes. So, you do not have any corrections for pressure or volume, and we get the expression as PV is equal to RT. So, there are two conditions here, that is when low pressure and high temperature. So, when pressure is low and temperature is high, when these two combinations come together, real gases tend to be ideal. Okay. Now, we will go for another case, that is the exceptional behavior of hydrogen and helium. You have seen that PV against P graphs, hydrogen and helium only has the rising part, they do not have a dip in their PV against P isotherms. Okay. Now, when hydrogen and helium, as we know, it is in the beginning of the periodic table, their atomic masses are very low and their sizes are extremely small, and therefore, they have very small intermolecular forces of attraction. As a result, if they have very small intermolecular force of attraction, the pressure correction A by V square can be neglected. Now, the equation takes a form P into V minus B is equal to RT, expanding P into V is PV, P into minus B is minus PB is equal to RT, and rearranging we get PV is equal to RT plus PV. So, instead of PV equals RT, It is greater by a factor Pb, and therefore, we have a only rising part in the case of helium and hydrogen. So, these are the conditions we see for applicability of van der Waals equations to the real gases. Now, let us move on to the next question. State virial equation of state and explain the terms involved. The virial equation of state, we have it in two forms. One is in terms of volume, the other one is in terms of pressure. In terms of volume, the expression is PV is equal to RT into 1 plus B by V plus C by V square plus D by V cube plus E by V to the power 4 and so on. Here B, C, D and E are virials. This is second one, do not confuse it, this is second one. Then next one is the third, fourth and the fifth coefficients. They are known as virials coefficients, that is virials, second, third, fourth and fifth coefficients. Now, in terms of pressure, virial equation PV is equal to RT into 1 plus B prime P plus C prime P square D prime P cube plus etc., where B prime, C prime and D prime, they are virials. Again, this is the second one and next is the third one and this will be the fourth coefficients, virial coefficients respectively. Okay. We will move on to the next question. Explain the term boil temperature of a gas. Now, here we will be explaining it in terms of virial equation. Boil temperature Tb is the temperature at which the second virial coefficient B for a gas becomes 0. That is, when temperature is equal to Tb means that is B should be equal to 0. The value of B will be equal to 0 and from that we can derive the expression as Tb is equal to A by Rb, where A and B are van der Waals constant and R is a universal gas constant. Now, let us move on to the next question. Discuss Andrews' experiments on the isotherm of real gas and continuity of states. Okay, we will move on to the answer. Andrews' experiment of pressure volume isotherms. Isotherm means each plot will be at a constant temperature. Now, here we have a plot of, you have to explain it, that is we are having the PV isotherm at 13.1 degree, 21.5 degree and at the critical temperature 31.1 degree Celsius. So, these are the curves and some of the curves above the critical temperature of carbon dioxide. These are for carbon dioxide. Okay. Now, we can see that is from here when this is here volume is high and therefore, this will be in the gaseous state, and when we come to this side when volume is reduced, that goes to the liquid state. So, here if it represents a gas over here, when I am going to, that is the temperature is maintained constant, that is isotherm 13.1 degrees Celsius, and I am going to increase the pressure when the volume decreases, and at a point y the gas starts liquefying. It is not wholly completed into in the liquid state, but instead we will have some part of the gas getting liquefied. So, here from y to x, in this place we will have gas and liquid coexisting and there is a discontinuity. You have some of the substance in the liquid state and some of the substance in the gaseous state. If this discontinuity is there, how can we consider that the gas and liquid to be in a continuous manner? So, that is what we are going to find out. Now, here this is we are having a region when gas and liquid coexist. Now, at the point x, the whole of the gas gets converted into liquid state, and after that there is no much difference in volume with applying very high pressures, very little change. Okay. Now, we will go to a higher temperature 21.5 degrees Celsius, where you can see that the gas represented by the point A remains in gaseous state till the point B. At the point B, it starts liquefying, and throughout this curve from B to C, both gas and liquid coexist. At the point C, the whole of the gas gets converted into liquid, and from there we have only the liquid state. Now, when we come over here, you can see that from this point up till the point represented by E, it remains in the gaseous state. You do not have a condition where we have the liquid and gas coexisting, and that means there is a discontinuity, that is 100% gas, that is totally gaseous state, and here we have totally liquid state, and in between there is a discontinuity between these two states, that is the coexistence of gas and liquid together. So, at this point we do not have such a case, that is at that particular point represented by the letter E, that is the point over here, the gas completely gets converted into liquid at that particular point. So, there is no discontinuity there, and there is a curve drawn joining the regions, and here it comes a single point, and this region which is colored in the blue color, we have the coexistence of gas and liquid together. Okay, so this is the area where there is a coexistence of gas and liquid, and so in all these regions you can take any other temperature in below critical temperature, you have the gaseous state getting converted partially to liquid, and there will be a region where liquid and gas coexist, but at critical point you do not have this discontinuity. You can say the gas at a particular point gets completely into liquid state. Okay. So, that is about what they have said in this. Then the temperature at which we found that there is a point at which where the gases, that is here it is carbon dioxide, has been completely converted into liquid state, and that temperature is 31.1 degree, and above that the whole system, you can see in the graph, there is no formation of liquid, it remains only in the gaseous state. So, the temperature 31.1 degrees Celsius for carbon dioxide, if you go any temperature above that, you cannot liquefy carbon dioxide, and this temperature is known as the critical temperature of carbon dioxide, because above that temperature whatever high pressure you give, the gas gets never liquefied, and the corresponding pressure is 73 atmospheres at 31.1 degrees Celsius, and that is known as the critical pressure, and volume of 1 mole, that is the molar volume at critical temperature and critical pressure, is known as the critical volume of carbon dioxide, and it has been found that it is equal to 95 centimeter cube. Now, we will explain the continuity of state. We will take another graph. Okay. Here you can see this is a plot when the temperature is below critical temperature, and this is when temperature is equal to critical temperature, and this is the region which we have shown there where we have gas and liquid coexisting. Okay. So, at critical point we feel that there is no discontinuity, that is once just at that point, just before that point it is totally gas, and just at that point it gets converted into liquid state, and there is no discontinuity at all. Okay. Now, we can consider, that is continuation of gaseous state into a region of very strong intermolecular attractions and smaller volumes is the process taking place at the critical state. Now, let us see if we do not go to a critical state, can this be possible? Now, here we are going to take, that is a gas represented by the point A on this isotherm. that is below critical temperature. Now, what I want to do is, I want to increase the pressure of the gas, but volume is maintained constant. Volume should not change, but pressure should increase. For that, I will raise the temperature till the point L. Okay. Once the point L has been reached, the pressure is maintained constant, and what I am going to do is, I am going to reduce the volume, and finally the system reaches the point D, and point D is the condition when it is totally liquid. So, you do not have, that is, as the system crosses this point, it gets completely liquefied. So, we did not reach the critical condition, but without that itself, you can convert a gas completely into liquid without having any discontinuity between them. So, it is assumed that we can consider it is a continuous, that is, from gaseous state to liquid state, it is a continuous one where we have the gas getting converted into a state where there is more intermolecular force of attraction and lower volume. So, that is what we say about the continuity of state, and that is what it is, a continuation of gaseous phase into a region where there is a strong intermolecular force of attraction and smaller volume. So, next is we will pass on to the next question. Define critical temperature, critical pressure and critical volume of a gas. The temperature at or above which a gas cannot be liquefied regardless the amount of pressure applied is known as critical temperature, denoted by the letter T with a subscript C. The minimum pressure you have to apply to cause the liquefaction of a gas at critical temperature, that is very important, at critical temperature is known as critical pressure, or you can represent it as P with a subscript C. The volume occupied by, very important, it is not simply volume, it is a volume occupied by 1 mole of a gas at critical pressure and critical temperature is known as critical volume, or to be more appropriate, you can call it as critical molar volume, because that is a volume of 1 mole. Okay. And it is represented as capital V with a subscript C. Now, critical temperature, critical pressure and critical volume of a gas are known as critical constants. Okay. Let us move on to the next question. The van der Waals constants for gaseous HCl, A is equal to 0.367 newtons meter raised to 4 mole raised to minus 2, B is equal to 4.08 into 10 to the power minus 5 meter cube mole inverse. Find the critical constants. What are the critical constants? Vc, Pc and Tc. We know the relation between the critical constants and van der Waals constant, and using that you can derive the critical constants. Okay. These are the data given. A is equal to 0.367 newtons meter raised to 4 mole raised to minus 2, B is equal to 4.08 into 10 to the power minus 5 meter cube mole inverse. And first we will be seeing Vc. Vc is equal to 3V, that is the expression. Now, that means Vc is equal to 3 into B. B means 4.08 into 10 to the power minus 5 meter cube mole inverse. So, multiplying that you will be getting it as 12.24 into 10 to the power minus 5. There is no change in unit, it is meter cube mole inverse. Okay. So, next is we have to find out Pc. Pc, the relation is Pc is equal to A by 27 B square. You will have to by heart all these things, otherwise you will not be able to do the problems. And Pc will be equal to, what is A? A is equal to 0.367 newtons meter raised to 4 mole raised to minus 2, and by 27 B square. B is 4.08 into 10 to the power minus 5 meter cube mole raised to minus 1 whole square. Now, let us see what will be the unit. Here 27 doesn't have any unit. Here it is meter cube, but you have the square. So finally that will be meter raised to 6. Now here we have mole raised to minus 1, square becomes mole raised to minus 2. Okay, the rest is okay. Now here mole raised to minus 2 and this mole raised to minus 2 get cancelled. Here meter raised to the power 4 is there. So this becomes meter to the power 2. Okay, and Newton will be there in the numerator. Taking meter square to the numerator, it becomes meter raised to minus 2. So the unit will be newtons per meter square, and just solving using a good scientific calculator, you can find the answer as 8.1654 into 10 to the power 6 newtons per meter square. That is PC, and last one is the TC, that is the critical temperature. The relation is TC is equal to 8A by 27 RB. Now here we don't have the value of R, it is not given, only A and B, that's the van der Waals constants are given, and therefore we will have to choose R appropriately. Now you can see the units of A, B and all in SI units. See, it is all in SI units. So the value of R should be chosen in SI units, and that is equal to 8.314 joules per Kelvin per mole. This is very important, choosing the value of R. Now TC is equal to 8 into A is 0.367 into Newton meter raised to 4 mole raised to minus 2. Then 27, R is equal to 8.314 joules per Kelvin per mole inverse, and B is equal to 4.08 into 10 to the power minus 5 meter cube mole raised to minus 1. Now we will have to see how the units get cancelled, that is meter cube and this meter, okay, get cancelled. Okay, mole raised to minus 2 and mole raised to minus 1 and mole raised to minus 1 get cancelled with mole raised to minus 2. Now we have Newton's meter, then here joules is there, it gets cancelled with newtons per meter, so that is also gone. Now finally we have the Kelvin, which when taken, that is Kelvin inverse, so just taking it to the numerator, it becomes Kelvin, 320.5694 Kelvin. Now let us move on to the next question. How are the critical temperature, critical pressure of a gas determined? Critical temperature and pressure, they are measured simultaneously. So here we have the determination of critical temperature and pressure by Cagniart-de la Touze method. The principle behind this is there is a meniscus which gives the distinction between the liquid and gaseous phases disappears at critical state. So the disappearance of meniscus can be taken as the critical state. Now the apparatus is shown here, that is we are having gas bulb in which we enclose the substance in the liquid state. It is connected to a manometer to measure the pressure, okay, and thermometer to measure the temperature, and the whole apparatus is kept inside a jacket where we can alter the temperature of the bath. It can be either water or any other liquid, and this temperature of the bath will be the temperature of the gaseous substance and the liquid within the bulb. Now what we do is we gradually increase the temperature. Now the temperature is increased, the liquid starts getting converted into gaseous state, and a temperature will be reached when the meniscus between the liquid and the gaseous state just disappears. Now we will note the temperature at which it disappears and also the pressure from the manometer as PD. Next we will cool down the gas, and there will be a particular temperature at which the meniscus appears. So I put it as TA, appear, this is for disappearance, and the corresponding pressure at which the meniscus appears is also noted. Now, taking these values, you can calculate Tc as Td plus Ta divided by 2, that becomes the mean, because you can avoid the experimental errors. For that, we are going to take the two temperatures and take the mean, that will give you the critical temperature. And in a similar manner, we take the pressure values of disappearance and appearance of the meniscus and take the mean, you get the critical pressure. Now, let us move on to the next question. How is the critical volume of a gas determined? That is, determination of critical volume is very difficult, because at critical conditions, at critical state, we know that it is the point at which the gas suddenly gets converted into liquid. Okay, or you can say that at that condition, the volume of the gas or the fluid at critical condition, it will be very high, and it is sensitive to what? Changes, small changes, even small changes of temperature and pressure, and small variations or small errors in temperature and pressure will be causing a change, a drastic or a very high changes in volume changes, and therefore, the measurement of volume, that is at critical condition, is very difficult. To get it accurately, we follow Amagat's method, which is based on the theory, that is Cailletet and Mathias' law of rectilinear diameters, which states that mean densities of any substance in the states of liquid and saturated vapor at the same temperature is a linear function of temperature. Now, these two densities, that is of a liquid and the vapor in which it is in equilibrium, is known as orthobaric densities. You can say that mean of orthobaric densities is a linear function of temperature, and it can be represented by a mathematical expression. dl stands for density of the liquid, dV stands for density of the vapor with which it is in equilibrium, divided by 2 gives you the mean. Okay, is equal to A plus BT. A and B are constants, and this is an expression for a straight line, and therefore, we can say that the mean of density is a linear function of temperature. Okay. Now, we are going to take a gas, not gas, a liquid and a gas together in a graduated tube. Here there will be graduations. Okay, I will take the liquid, and it is a known mass. Mass is known, and I will keep this at different temperatures, and I will be measuring the volume of liquid and volume of gas in equilibrium. Okay. Now, from these at different temperatures and for different masses for a given temperature, you can use the data to solve for the densities of liquid and densities of vapor at a given temperature. So, we will give at different temperatures, we will be finding out the density of the liquid and density of the vapor. And now, we can plot a graph. See, so this temperature, this is for the gas, because density is low for the gas, these are for the gases, and these are for the liquids. They will be having a higher density. Now, these values are plotted. You can get a graph over here, but if I extend this graph, you have a curve with flattened peak, and you will not get an exact value corresponding to that temperature. Now, here is where we use law of rectilinear diameters, in which what we do is we take the mean of these two, you will get this point, again the next one, and taking these mean of densities of gas and liquid, or you can say they are the orthobaric densities, and I can plot a line, can draw a line, and you can see that it is a straight line. Okay. Now, extending that, it meets at the curve at the point C, and this is the critical condition, and the density corresponding to that will give you the critical density. Now, critical volume Vc is equal to molar mass by critical density, because you can't take any mass because critical volume is for 1 mole. Okay. So, molar mass divided by critical density will give you the critical volume. Next is, what is supercritical carbon dioxide, and give its applications. Here, supercritical carbon dioxide is a carbon dioxide which is in a fluid state and has the density of the liquid but behaves like a gas. It is non-toxic, non-flammable and environmentally friendly gas. Now, what are the applications? It is an eco-friendly solvent because it is very cheap, inert, readily available, non-toxic, non-inflammable, and it is capable of solubilizing lipophilic substances, and also it is considered as non-polluting in comparison to other organic solvents. Okay. Now, using supercritical carbon dioxide as a solvent enhances the quality of the products, because the products will not have any residues from the solvents, and therefore it can be used as a solvent for several polymerization reactions, polymer modification reactions, etc. Besides, removal of the solvent is very easy. You just depressurize it and the carbon dioxide goes to the gaseous state, escapes from the substance, and you can reuse that carbon dioxide. It is supercritical solvent extraction is possible because they have low viscosity but high diffusion power, and therefore it is a very good solvent for extraction and mainly used for extraction of caffeine from green coffee beans, extraction of essential oils and pharmaceutical components from the plants. It can also be used as a solvent for dry cleaning, because in dry cleaning we use organic or petroleum solvents, and that can be avoided if you use supercritical carbon dioxide. Next is impregnation and dyeing. Since it has got very low viscosity and high diffusivity, supercritical carbon dioxide can be used into some porous material to introduce certain substances into it, like dyes or anything to improve the characters of that particular compound. And supercritical carbon dioxide is used to deposit dyes into polyester and polyamide materials. Then introducing pharmaceutical drug components into certain polymers, then pesticides into wood and wood-like materials. All these can be done using supercritical carbon dioxide. Next is in power generation, because we know that from Carnot cycle, the temperature difference between the source and the sink determines its efficiency. And carbon dioxide is considered as a very good working fluid in power generation as well as refrigeration systems. It has an advantage because it has got a low critical pressure than water, but a slight issue is that with the corrosion, because that is slightly acidic. Now, in geothermal plants also, instead of using water, you can use supercritical carbon dioxide as the working fluid. Next is supercritical drying. When we use supercritical carbon dioxide, since it is having good diffusibility and all, its surface tension is very low, or you can say that surface tension is negligible. Now, when surface tension is present in the solvents, when we extract certain delicate samples like biological samples or archaeological samples, what happens is when we try to remove the solvent from it, the surface tension of the fluid drags small structures within the solid, causing some distortions, or in some cases it shrinks. Since carbon dioxide does not have, supercritical carbon dioxide does not have surface tension, you can have the structures intact. At the same time, you can remove the solvent like that and keep it dry. And that's all for this question and answer session. I haven't discussed the derivation of van der Waals equation, which is also an important question in this topic, which requires a larger time, and therefore I have avoided. That's also an important topic. So that's all for today. Thank you.